right, good morning. If you're watching this, you're probably trying to get some credit. So, as usual, to get the credit, as I'm watching the video, I'm going to give a random set of attendance words. You're going to want to write those down every time I say one of the attendance words. Also, take a screenshot every time I say one of those attendance words. And then at the end of the video, send me an email that includes the list of words, the accompanying screenshots, and also one question about the material covered in the lecture. And that's it. Well, the first word for you for the video then is going to be due, D-U-E. So I should see a screenshot too that shows a picture of me pointing at this word due, D-U-E. That's it. It is 7:49, so if you want to, you can skip ahead probably about 6 minutes, 6 or 7 minutes, and that's when the lecture will officially begin. Morning. Right. You have a good weekend?
Yep. Did you?
It's all right.
It's finally gonna warm up this week.
Yeah. I still have just the smallest amount of snow in my yard.
Yeah, we
And,
got that.
where it's shaded. Yeah. Morning.
Ashley, right?
Yep. And Isaiah. Did you guys have a good weekend? Morning. It's Kaylee, right?
Yes.
That was your weekend. Uneventful. This is good. It was neutral. Thank goodness here. Excuse me. Yes, and it's here. Isaiah's here. Isaiah's already. Isaiah just came in, but Lucas is here. Sorry. Yeah. All right. Less than 3 minutes left, so I'll go ahead and start since some of this is just repetitive stuff. Anyway, so exam one is now past due. My plan is to reopen it today. We'll see. I just need to check a few things, make sure like everyone's taken it. No one had any issues over the weekend. But assuming everyone has taken it and there were no issues, I will reopen it today. You'll be able to retake it as many times as you want. The retake is open book. The retake is untimed. And you have nothing to lose, right? Because the only thing that will happen is if you get a bad score, just don't tell me about it and just keep your original higher score. But if once you are satisfied with your new grade, email me. You have to email me because I won't know without that. Email me and let me know that you're done, and then I'll average your first grade with your highest grade. If that makes any sense. If not, we'll talk later. So any questions about exam one? All right. So since exam one is now past us, we are starting on exam two stuff today. So everything moving forward will be on exam two. Oh yeah, really quickly to remind you, speaking of exams, the final exam is going to be about 100 questions. About 50 of them are from the first 3 exams. So this exam that you just finished, that you're now allowed to retake, is basically part of your study guide for the final exam. So even if you got a good grade, it really would help you to retake this exam Just keep retaking that, right? Get that practice in. Again, even if you had a great grade, that'll help prepare you for the final exam. So please take advantage of that. But anyway, yeah, so we started exam 2 stuff today. Any questions about exams at all? Okay, as usual, I'll remind you that attendance is mandatory, participation is graded. I do change up how you get the participation points because I want to keep you on your toes and make sure you're paying attention. So today, you're going to write down all the attendance words that I give, and sometime before 9 a.m. after the lecture, send me that email with a list of attendance words and 1 question about the material covered in the lecture. So any questions about all that? All right. I will take attendance and then we'll get moving. Bear with me, I'm exhausted for some reason. I didn't get good sleep. So if I'm dragging, I apologize. Anyway, Ashley's here. Barrett is here. Wooten is not here. Strahan is not here. Dickens is not here. Clark is not here. Inca is here. Isaiah is here. Copes not here. Smith is not here. Caden Watson not here. Kaylee is here. Lucas is here. Marley is not here. Noah is not here. Savannah is here. Mia is here. Edwards, Edwards is here. Wilkes is not here, and Trahan is here now. Did I miss anybody? All right. Let me make sure I have Trahan marked as present when we get started. There we go. All right. So again, make sure you send that email with the attendance words and the I have 1 question about the material today. First word for attendance would be president, since it's President's Day. Okay. So let's get jumping. So this is chapter 4 that we're starting. This is actually a very important chapter. This is how cells obtain energy. And if you remember back in chapter 1, when we talked about those properties of life, we talked about one of them was the fact that things that are alive convert energy from one form to another, right? We have this energy conversion. That's one of those properties of life. It's one of those things that makes us alive, which is why one of the reasons why this is so important. Also, like I said, when we rushed through chapter 3, remember I said a lot of that stuff, I'm going to rush through it because you're going to learn about these parts later. And this is later, right? So we really quickly talked about the mitochondria, for example. We very quickly talked about the cell membrane. But now all that stuff's going to be a little bit more important for me to talk. So here we go. Pour this up again. What's going on here? All right. This is broken down in this quite a long chapter, right? It's broken down into these 5 portions: energy and metabolism. Then basically these 3 things right here. Excuse me, these 2 bullet points, 4.2 and 4.3, that's basically something called respiration. And a majority of the exam, at least for this chapter, is going to be covering respiration. And we'll talk about that when we get there. Then we're going to talk about fermentation, and then finally we'll talk about connections to other metabolic pathways. So again, this whole thing is basically about how your cells get energy. Almost the entire exam. So exam 2, again, which starts today, the stuff we're learning today is going to be on exam 2. And that might even be a test question. What's this exam about? This exam, exam 2, is all about energy, right? So now you're going to learn how your cells convert energy, basically through glucose. We'll talk about that. But then later, we'll talk about where did that energy come from? Where do we get the energy and glucose? So we'll talk about that in the next chapter. But anyway, let's get into it. So 4.1, your learning objectives. By the end, you should be able to explain what a metabolic pathway is. You should be able to state the first and second laws of thermodynamics. You should be able to explain the difference between kinetic and potential energy. You should be able to describe endergonic and exergonic reactions. And finally, you should be able to discuss how enzymes function as molecular catalysts. So some of this might be a review for a lot of you, but we'll see. The first term you need to know is bioenergetics. I'm probably not going to ask you that word. I'm not going to ask you like a vocabulary word, but bioenergetics, basically what we're talking about. Bioenergetics describes the concept of energy flow through living systems. So like I mentioned, when we first talked about this in chapter 1, and when I said this is one of the properties of life, I said, you need energy to live, right? You get that energy through food. But ultimately, all that energy, for the most part, came from the sun, right? But you can't get it directly from the sun, right? You can't just go out naked and sunbathe and collect that energy, right? You need to eat food. But ultimately, that came from the sun. And that's what this is all about. This is what this whole chapter, or this whole exam is mostly about. It's how we get that energy from the sun into you. If I were writing this textbook, I would have started with that first. I would start with photosynthesis and then go to respiration, but I didn't write the textbook, so here we are. I'm doing it the way the textbook does. The flow of energy is through a series of chemical reactions. That'll be very important. You're going to learn about some of those chemical reactions. I know at least one of you is thinking about taking Bio 120 after this, which is like the harder version of this. So as we go through this, you should keep that bullet point in mind, because I'm going to be teaching in these chemical reactions, but I'm not going to be naming them. And then when you take 120, you're going to need to know the names of all of these chemical reactions. Of course, you guys will learn some of them, but there will be more that I won't name. Anyway, all the chemical reactions that take place inside of a cell, this is known as metabolism. That is a word you do need to know for the exam. One, because it will be used to ask other questions, and two, there might be a question where I ask you, what is metabolism? So metabolism is all the chemical reactions that are happening in your cells. And that's why we got a whole long chapter on chemistry, right? This is biology. You have to take a chemistry class or chemistry chapter, and that's why. Biology is basically applied chemistry, right? It's the chemistry that's happening, the chemical reactions that are happening in your cells. Without it, we wouldn't be alive. Any questions about this slide? All right. So let me know if I'm going too fast or too slow, by the way. So speaking of metabolic reactions, they are broken down into two different types. You should know this for the exam too. You have anabolic and catabolic. Anabolic reactions need energy because they're building new molecules. And I guess maybe a way that you can remember that is I always remembered anabolic steroids, like when weightlifters or certain athletes would abuse steroids to get larger, to build mass. Anabolic. So I always remembered building mass as anabolic, just building something. The opposite of that is catabolic. So this does not need energy. This produces energy because you're breaking these molecules down. This goes back to what I said back in chapter 2 when we first started talking about chemical reactions and molecules. I said, however much energy it takes to build a molecule, that's how much energy will be released when you break it down, for the most part. And not all molecules are the same. So some molecules are harder to assemble. They require more energy to put them together. And again, the more energy it takes to assemble them, the more energy that will be released when you break them down. Either way, whether you're talking about anabolic reactions or catabolic reactions, you have to have enzymes for these things to happen. Almost none of them happen without these enzymes. And we talked a little bit about enzymes before in chapter 2 when we talked about proteins. Right? And I said there's different types of proteins, but one of the most important ones for us academically, like for this course, would be enzymes. And I said we'll be talking about them later. Here we go. We're starting to talk about them again. So again, to remind you, enzymes are proteins that have very particular shape, and they're very specific, and they make very specific chemical reactions happen. So it's not like there's just one enzyme that makes anabolic reactions happen, and then a different enzyme that makes all catabolic reactions happen. There's one enzyme for every single little chemical reaction, for the most part, that happens in your cells. Anyway, any questions about this slide? All right. So again, just before I move forward, I want to remind you, you need to know the difference between anabolic and catabolic. I gave you a way to remember anabolic. All right. The way you can remember catabolic, I don't know if any of you have ever had cats. A lot of times they like to just swipe stuff off the table just to watch it fall or break. So that's how sometimes I remember catabolic is breaking things down. Hopefully that helps. Anyway, that brings us to another term. It's a lot of terms, at least at the beginning of this chapter. Thermodynamics. I might ask you what this is on the exam. This is the study of energy and the energy transfer involving physical matter. So not just energy itself, but this is transfer of energy from one thing to another. When I clapped my hand, that was actually a lot of transfer of energy. There's a lot of chemical energy being converted there, so I could move my muscles, and then my hands hit together like that, and you could hear it because that was kinetic energy that vibrated the air, and that air vibration hit your ears, and then that was converted to an electrical signal that was sent to your brain. Right? It's really complicated, but it's kind of stuff we'll be talking about in this chapter. So thermodynamics is the study of energy and the energy transfer. Then what is energy? And there's another term you need to know for the exam. Energy is the ability to do work or to create some kind of change. Right? So we're using energy right now for the HVAC in this room to keep it relatively warm, right? We're changing the temperature in this room so it's warmer than it is outside. These are some examples. I'm not going to ask you any of these examples, but you're probably already familiar with them. Electrical energy, right? Like I said, we're using electrical energy right now to change the air temperature. Heat energy, which when we think about electric energy, that's interesting because John Amos, right, the power plant right down the road, it's burning coal to produce heat, and then that heat makes steam, and that steam turns a turbine, and that makes electricity, and that electricity comes here, and then we use that electricity to create heat. Light energy, right? We're looking at this. This is light energy. Light energy is going to be very important, more so in the next chapter, right? Because basically, like I said previously, almost all the energy on Earth, at least for living systems, comes from the sun. Ultimately, there are a few exceptions. But anyway, so if it all came from the sun, obviously light is going to be very important. Chemical, also very important. That's basically all we're talking about for this chapter is chemical energy. Right, this idea of how we eat food and break it down and release that chemical energy and then use that chemical energy to do other things, right? It's all about chemical energy. So yeah, these last two are very important, and these are the ones we'll be talking about a lot during this this whole exam portion, this section of the course. So any questions about this slide? Okay, the next word for attendance will be heat. Heat is the next word for attendance. The second word for attendance, if you keep track, or if you're watching the video, the third word for attendance, because I had one for prior to you guys getting here. All right, let's move forward then. So talking about thermodynamics. There's some laws about thermodynamics. You're going to need to know these for the exam. It's a lot of information I'm giving you guys for the exam. I apologize for that. It's just the nature of this chapter. Thermodynamics. The first law of thermodynamics states that energy can be transferred from one form to another, but it cannot be created or destroyed. So you do need to know that for the exam and just in general. I have a little star there to remind myself to tell you that your textbook defines it differently. And there's no need to memorize the definition, just understand the concept. So the textbook definition is worded differently, but it says the same thing, right? The concepts are the same. I mean, for that matter, for the most part, that's good advice for this entire course. Just because I say it somewhere, I don't want you to just be able to memorize it and spout the words out. You should understand the concept. Yeah, but anyway, that's important. When you do have your next pre-lab, because remember there was not one due on Friday, past Friday, but there will be one due this Friday, and it's about photosynthesis and respiration. And one of those questions for the pre-lab asks you, in these experiments, are these algae creating energy, or are they converting it from one form to another? And the answer is they're converting it from one form to another, right? Because energy cannot be created or destroyed. We can only convert it from one form to another. And life depends on this conversion, right? So again, like I said earlier, this is a property of life. This is one of the things that makes us alive, is the ability to convert energy from one form to another. Another important concept is this second law of thermodynamics, which states that energy is lost, right? So in the first law, we're saying that energy can be transferred. In the second law, we're saying every time you do transfer that, you lose some of that energy. And just so you know, and you will need to know this, I should have written it down. Maybe I have it written down somewhere else. When it gets transferred from one form to another and we lose that energy, it's almost always lost as heat. So if you have a question on the exam that says something like, the kid was riding his bike and he applied the brakes Where did all that kinetic energy go? You could say most of it was lost as heat. Now, granted, he's probably not going to feel it, but I guarantee you, if you were to feel the brakes right after he did that, it would be warm, right? So again, energy can't be created or destroyed. It just gets converted. And when we do convert it, we always lose some. And when we do, it's almost always as heat. That will be important. Later in this chapter, I'm going to give you a specific number that you're going to need to know for the exam. And you know, hopefully by now, I'm not very big into numbers, but that's one of those few times I don't want you to know the number. Anyway, any questions about this side? Yes, sir.
Yeah, let's see, form for the second one, from one form to another.
From one. Yep. Good eye. So yeah, that should say form. Thank you. Hopefully I don't brain dump that. If I can remember that by the time I get to my office, I can fix it. I barely had my coffee, so we'll see. All right. Any other questions? All right. So we've already talked about this. And I know there's nothing up there yet. But can someone tell me really quickly, what is heat? Like when I say I'm increasing the heat in here, what do I mean? At the molecular level, what do I mean when I say I'm turning up the heat? The heat is increasing in this room. What does that mean at the molecular level? Because I've already said it. See if anyone remembers. For extra participation points, who can answer that? What is heat at the molecular level? You guys are just being shy. There's no way none of you remember this. I think all of you remember it. You're just afraid to have a bad answer. We'll just move forward. But I remind you, I love bad answers. Because if you're wrong, then I know where your brain's at, and I can help you get from where you're at to where you need to be. If I have no idea where you're at, I can't guide you to that point, right? So I love wrong answers. Anyway, heat. Heat is a type of kinetic energy, right? This is the energy of matter, of motion. That's all heat is. So when I say we're turning up the heat in this room, what that means at the molecular level is the air molecules are moving faster. That's the most important thing that you need to know for the exam and to understand the concepts beyond this point. The last two bullet points here, it's true, but not very important academically for us, not at this level of biology. It is the most chaotic and disordered form of energy. I probably won't ask you that. And like I said previously, every time you convert energy from one form to another, it almost always generates at least some kind of heat. Just like when you have, you have your computer plugged in, and you have an AC/DC converter, because the electricity coming out of the walls is AC, but your computer needs DC. When you hold it, it's probably a little bit warm because you're converting that energy from one form to another. It's still even just from electric to electric, but it's from AC to DC. Another thing that's really, really important, but not for you guys, but it's in the textbook, so I'm including it, is entropy. Entropy is really important because when you talk about energy and metabolism and all the stuff that we do here, when you really study it, there's a lot of math equations involved, but we don't do that. So for you guys, this is pretty much useless, I think, but it's in the textbook, so I'm including it. I'm probably not going to ask any questions about this on the exam, but really quickly, let's talk about it. Entropy is the measure of disorder or randomness in a system. And every time energy is converted from one form to another, entropy increases. So there you go. I told you. I read it to you. That's the end of it. You do not need to understand entropy to understand anything I'm going to teach you after this. But again, especially for those of you, the one of you that's going to take 120, the harder version of this class, when you talk about energy, there's chemical equations and they're mathematical, which is good because you're a mathematician. But anyway, everything is accounted for in these equations, right? The energy that's gained, the energy that's lost, the mass, the entropy. So this is an important concept in life. But for Bio 101, academically, it's a very unimportant topic, concept. But anyway, any questions about this slide? All right, so this next slide, we're kind of going out of order a little bit. So to remind you, these PowerPoints are largely based on the old textbook. And then when we got this new one, I kind of just, instead of starting new, I just kind of edited the old stuff to match the new stuff. This is one of those times where I'm going a little bit out of order than what the new textbook does. So anyway, kinetic energy. You definitely need to know the difference between kinetic energy and potential energy. So there's kinetic energy. That is the energy of motion. So that picture on the right is a better example of kinetic energy than the picture on the left. I don't know if you can see, but on the left you have a dam. On the right, you have a running stream, right, down a mountain. But yeah, you definitely need to know kinetic energy is the energy of motion. So what is potential energy? For more participation points. Again, don't be shy. If you're wrong, I love a wrong answer. Unless if it was really wrong, we might just be lost. But does anybody remember what potential energy is? How would you describe potential energy? If a kindergartner said, "What is potential energy?" How would you explain it to them? Man, you guys are so shy. No one? Not even for extra points? Okay, there we go. Potential energy is stored energy. There you go. You need to know that. That's probably the more important energy, academically anyway, for this exam. We'll very much talk about potential energy. Like we have these molecules that have that stored energy. Then we break it down and release it. And then we just use that energy to make other molecules where we store that energy. And we move things, move things against the concentration gradient. So then we have stored energy, right? It's all very much about potential energy. Now, when you talk about potential energy, most people are very familiar with location, right? So if I were to ask you, which one of these has more potential energy? A or B? Which one has more potential energy? A or B? A, right? Because it's location. It's higher up. So gravity is going to do more once I release it. So everybody's really familiar with that. But unfortunately for us, that one's the less important. What's more important, and the one that people are less familiar with, is the potential energy of structure. And I've already brought this up before, and we'll bring it up a lot. You're going to be so tired of hearing it. Whatever energy that is required to build a molecule, to build that structure, that is the amount of energy that will be released when you break that structure. For the most part, as far as we're concerned, that's 100% accurate. So again, and then it's not easy, right? All molecules are different. So the more energy it takes to build it, the more energy will be released when you break it down. So are there any questions about this slide? All right, here's a picture from the old textbook. It gives a little example of this relationship between potential energy and kinetic energy. So within this system, this person right here represents the greatest potential energy, right? Because they're not going to get any higher than that, except maybe if they bounce. But anyway, generally speaking, they're not going to get any more potential energy than that. And then when they jump down, all that potential energy that's stored is converted to kinetic energy as they move. And then once they hit the water, at least in this system, that's the least amount of potential energy that they're going to have. And then they're converting that, they have chemical energy in them. They're using that energy to pull themselves up and crawl back up here. And that is kinetic energy, right? So then you're converting chemical energy, which is not even listed here, chemical energy to kinetic energy. And as they get higher and higher, that kinetic energy is being turned into potential energy. So that's, again, an example from the old textbook. I don't even think it's that important because, again, for the most part, when we talk about potential energy in this course, in this chapter, we're mostly concerned with structure, not location. This is all location. It has nothing to do with structure. So for the most part, again, we're more concerned with breaking things down and building and the energy involved in doing that. Anyway, are there any questions about that slide? Another thing worth mentioning too, just to help you remember, like I said, every time you convert energy from one form to another, you lose some in the form of heat. That's even happening here, even though it's probably, you probably don't even notice. They don't notice it, but technically once this person's moving through the air, that's creating a little bit of heat. Those air molecules are warming up a little bit. Once they hit that water, technically, that water is going to change the temperature just a little bit because you converted energy from one form to another. All right, let's move forward then. If you download the PowerPoint, you can watch this little animation that talks about energy concepts. And they use a bow and arrow as an example. And I like that, and I'm going to use that a lot for this chapter. So not necessarily a bow and arrow, but I'm going to talk about the crossbow. And you'll see why when we get there. So like I said, when we talk about potential energy, the most important thing for us in this course is this chemical energy, right? We're talking about the potential energy of structure, not location. When we talk about structure, or at least for us, we're talking about chemical energy, like I keep saying. However much energy it takes to build a molecule, that's how much energy will be released. And not all molecules are created equal. This is why I have this picture here. These people are struggling to bring these huge magnets together because they're both on the north end, so they're repelling each other, right? Just like your molecules that we talked about earlier, they have electrons on the outside. By the way, that's a very missed question on the exam. The outside of a nucleus of an atom has only electrons. No protons, no neutrons, just electrons. But anyway, they're electrons, right? They're negative. So these atoms, in a sense, don't want to be together. I'm really making things basic and I'm oversimplifying, but for us, that's fine. But because they repel each other, right? So it's going to take energy to squish those things together. And again, however much energy that it takes to push those things together, that's how much will be released when you break them down. And it's a little bit like this crossbow. I don't know if you've ever shot one or used one, but you have to use some energy to pull that thing back. And once it's cocked, like it is there, it's ready to go, right? That energy is stored. That's potential energy due to its structure. Once you pull the trigger, you're going to release that energy. But until then, that is stored energy. And that concept, that analogy, we'll come back to that. But that's just the introduction to it. So any questions about what chemical energy is? All right. Again, please tell me if I'm going too fast or too slow. This is another concept that we mentioned before. I think in chapter 2, when we were talking about fatty acids, I brought this up. And I'm bringing it up again. So it's just an example, but cells and gasoline engines use the same basic process to make chemical energy stored in fuels available to work. It's the same basic process. What I mean by that is what we do in our cells is basically the same thing that gasoline engines do, which is break down a fuel in the presence of oxygen, which creates energy and heat. So it's very similar. Just like in this example that you saw in chapter 2, this is what octane looks like, right? And this is the triglyceride. So those fatty acids are almost identical to octane, which makes sense because they do almost identical things. When we break those molecules down in the presence of oxygen, it releases energy. So are there any questions about that slide? Okay, so this is just an example, by the way. I'm not going to ask any questions about car engines, but it is a pretty good example to help you really help illustrate this idea that it's kind of universal. Here we are again. This is an image that shows what we're talking about, right? Here's octane again, right? Of course, this is a little bit different than the last picture, but anyway, here's octane. When you break it down in the presence of oxygen, you're releasing energy. That energy, at least for a vehicle, is used to make it move, right? To make the parts move, which makes the vehicle move eventually. In the process of doing that, you lose some energy from heat, right? And then the end products are carbon dioxide and water. So, I mean, there's other stuff too, right? So when you burn gasoline, I wish it was just carbon dioxide and water, but there's other stuff too. But that's the big one. And the same thing happens in your body. When you eat glucose from your food, you're going to break it down in the presence of oxygen. And when you do that, you're going to release some of that as heat energy. You're going to lose some of it. The rest of it, you're going to put to work, and you're going to make ATP. We'll get to that in a second. But the byproducts are carbon dioxide and water. So again, I'm not going to ask you questions about gasoline engines, but the idea here is it's very similar, right? Same thing with, if you were to have a campfire, when you're burning the wood, you're burning the cellulose. Could be a different picture there. The cellulose in the presence of oxygen, right? And you're putting off heat energy, and the byproducts will be carbon dioxide and water, among other things. Anyway, any questions so far? All right, this next slide is really important in that it's not in your textbook, and it's one of those few times that I test you from stuff that's not in your textbook. So if you're taking notes, you want to write this one down. At least that last bullet point, which we'll get to in a second. So cellular respiration is basically what this whole chapter is going to be about once we get to it. Cellular respiration is the energy releasing chemical breakdown of fuel molecules. So when you think of respiration, you probably think of breathing. Breathe in, breathe out, right? You breathe in because your body needs oxygen. You breathe out because your body needs to get rid of carbon dioxide. But when we talk about cellular respiration, which does need oxygen and produce carbon dioxide, it's different. This isn't like breathing. This is breaking down molecules to get that energy stored in the molecules themselves, in those bonds of the molecule. And the number that you need to know, again, it's not in your textbook. It's from the old textbook, and it's one of those few times that I test out of the textbook. And also one of the few times that I give you a specific number. But about 34% of that energy is converted to useful work. The rest of it is just lost as heat, which is why I have that picture, that infrared picture, the FLIR picture of this person. And that person's putting off heat. That's where the heat comes from. Your body should be about 98.6 degrees Fahrenheit. That's where that heat comes from. This doesn't come out of nowhere. It's not magic. It comes from you breaking down these molecules. So are there any questions about this slide? All right, the next word for attendance will be heat. Heat is the next word for attendance. So of course, if you're watching the video, there should be a screenshot of me taking, pointing at the word heat. All right, speaking of numbers, now we're about to get into some math here. Like I told you earlier, when I was talking about entropy, when I first introduced that concept, I said, for you guys, this is not important, but when you really start learning biology and you're looking at the chemistry of it, there's a lot of math involved. So now we're going to talk about some math equations, but we're not actually going to do any math. So don't be afraid if you're not into math. But here we go. There's these equations, and I'm not even going to give you the equations, but we're going to talk about some of the parts of the equation. So one of the parts of the equation is represented with a capital G, and this represents free energy. This quantifies the energy that's available for doing work after accounting for losses. So after we go from this, if you look at a chemical equation, start with these things, end with those things, what we're saying is once that's all said and done, how much energy is available to do work. That being said, there's two types of reactions. And this is kind of complicated if you read it. So before I read it, I'm just going to tell you the basic stuff that you need to know. Basically, for the exam, exergonic reactions release energy. Endergonic reactions require energy to happen. So I'll let you marinate on that for a second before I read this really technical stuff on the slide. But yeah, for the exam and to understand the concepts later in the chapter, in the semester, that's all you really need to know. Exergonic reactions release energy. Endergonic reactions need energy. Of course, they both need energy. You'll see what I mean later. And it's kind of in the name, so hopefully that'll be easy for you to remember. Like right? We're exiting. Things are getting put out, we're putting out energy. Endergonic, right? We need energy coming in. But anyway, that being said, really quickly, since it's in the textbook, I'm teaching it. If we were to do this, look at this as a chemical equation, which we're not. But anyway, what we do then, we would quantify this. So delta in math, delta generally means a change, right? So the change in G, right? Remember G, the amount of energy. Delta G is negative for exergonic reactions, again, which means energy is released. And that's the only thing you really need to know. Again, is the energy is released. I'm not going to ask about delta G. You just need to know that exergonic reactions release energy. Another way of saying that is the products have less free energy than the reactants. That kind of sounds weird, but again, think about what I said earlier. Not all molecules are created equal, right? So it takes energy to build these molecules. So what I'm saying is if you have like a really energetic molecule, that's your product, or should be a reactant, then you break it down in a chemical reaction. Now you have two new products. Those new products don't have as much energy as the original, right? Because you released that energy that was stored in making it, right? When you broke it down, you release that energy. So what you have left has less energy than what you started with. Another thing to keep in the back of your mind, and I'm not going to test you on this, but this is good to keep in the back of your mind, is that these exergonic reactions are technically spontaneous, which doesn't necessarily mean quick. But what I mean by that is like you don't necessarily need a lot of energy input to start it. And that'll make a little bit more sense later. Anyway, endergonic reactions are just the opposite. Delta G is positive, which means it's taking up energy. The products have more free energy than the reactants. So it's like, again, the opposite of what I was saying here. With that situation, you have these two molecules or atoms, whichever it may be in the situation, and they don't have that much energy. And when you put them together, and all that energy that was required to put them together, right, in the chemical reaction, then the product is whatever it is that you just made. And that product has a lot of stored energy, right? However much energy it took to make it, that's how much energy is stored. But also, these are non-spontaneous. These endergonic reactions, by definition, right, they absorb energy. They need energy to be able to have. So anyway, any questions about this before we talk about this last simple but very important bullet point? Okay, so regardless of the overall equation, right, even if it's putting out energy or absorbing energy, regardless of that, you're still going to need something called activation energy, which is what we're about to talk about. And that's, that makes a lot of sense when you think about endergonic reactions, because by definition, those reactions require energy. So yeah, of course you're going to need some energy. But it's a little bit trickier when you think about exergonic reactions, because you're thinking, all right, well, if that's releasing energy, then why does it require energy to start? And that's what we're talking about. Activation energy. So activation energy, as you're going to need to know for the exam, is the energy invested to start a reaction. Basically, and again, I'm giving you a vocabulary word, but I don't care for you to memorize the words verbatim. Just understand the concept. What I'm saying here is, regardless of what kind of chemical reaction you're talking about, whether it gives off energy or takes energy, it's going to need a little bit of energy to start. And I'm going back to this concept. So you have all that stored energy in that crossbow. It's ready to go, but it's not going to just spontaneously shoot itself. You're going to need to pull that trigger. And once you do, that's going to release that potential energy. That arrow is going to go flying, and it's going to become kinetic energy. And that's going to put off a lot of energy, right? That reaction, if it was a chemical reaction, would be an exergonic reaction, right? Because you're going to release a lot of energy. But nonetheless, you still need to put some energy into it to get it started. And that is activation energy. The next slide I'm going to show you is from the old textbook, and I think it does a better job of explaining it than this, but I like to explain things in different ways if I can. So are there any questions about this slide before I give you another visual of activation energy? All right. So you can almost think of it like this, right? So here we have a reactant. This would be an exergonic reaction right here, because the reactants have more energy than the products, right? More potential energy. And what we're doing is basically we're breaking it down, but I still like the fact that they have them elevated, because in a sense, you could almost think of it like we're pushing it off the cliff, and then once it hits, it breaks, right? So these two chemical reactions are the same, the one on the left and the one on the right. The only difference is, you can see here, to get this thing pushed off the cliff, we've got to get it over this little wall, so to speak, right? So that thing is blocking that molecule from going. So what activation energy, that's represents activation energy. And here's finally, for the first time that I can think of, when I'm telling you what enzymes do. So now, and this is important, this is how enzymes work, and this will definitely be a test question. Enzymes work by lowering the activation energy. That will be important. We're going to be talking a lot about that. But that's what enzymes do. Now, they do that in different ways, and we'll talk about that later. But in general, that's what they do. They lower the activation energy. So again, the chemical reactions on the left and the right are equal. The starting energy is the same. The ending energy is the same. The energy that was released in the reaction is the same. The only thing that's different here is because of the enzyme. This reaction on the right requires less input of energy. And again, every single chemical reaction in your cells has a specific enzyme for it. And without it, for the most part, they just wouldn't happen. So it's obviously very important. Any questions about this? Okay, this is from the old textbook. Your new textbook, I think it's a little too technical, but there it is. It's basically showing the same thing. Right, here we have reactants, products. In this case, we're looking at a endergonic reaction because the reactants have less energy than the products. So again, we're trying to squish things together, right? These the chemical reaction, we're bringing things together, which is going to require this energy. But again, you have activation energy for that. But with an enzyme, you have less activation energy. But anyway, yeah, it's the same concept as the last slide. I think it's just a little bit more technical, maybe a little bit more confusing. I guess it depends on how your brains work. But again, the last slide I showed you was an exergonic reaction where we were giving up energy. This one's endergonic. Either way, you're still going to need that enzyme to lower the activation energy. So are there any questions about that? Okay, let's talk a little bit more about how enzymes work. Like I've already mentioned, they're very selective. So again, for the most part, you can think of every single chemical reaction that happens in your cell has its own enzyme. So one single protein for that one chemical reaction. And there's all kinds of chemical reactions that are happening in your cells. So it's a lot of proteins, right? And that'll be important later in the semester, because later we're going to learn how DNA, we've already learned this, but we're really going to learn later how DNA has instructions on how to build proteins, right? So basically that's how you stay alive, right? Your DNA, for the most part, is just instructions on how to build these proteins. A lot of them are these proteins, these enzymes. Anyway, some terms you're going to need to know, maybe because I'll ask you about them, but definitely because I'm going to use these terms, so you're going to need to know them for that. Enzymes work on something called a substrate. So like I keep saying, they're very specific, right? There's a very specific enzyme for a specific chemical reaction. And when I say that, what I mean here is that the enzyme, right, it works on the reactants, right? In a chemical reaction, remember, you have the reactants and the products. The substrate is the reactant. Enzymes have something called an active site, which is demonstrated in this picture below here. That kind of looks like a puzzle piece, right? It looks like a round thing that's missing a piece that's round and then sharp, round and sharp, right? And remember, when you first learned about proteins, I told you more than any other biological molecule, it's all about the shape, right? It always is about shape for all molecules, but especially for proteins and especially enzymes, which is just one type of protein. It's all about the shape. So they have this thing called the active site that has a shape and a chemistry that fits the substrate. So again, that's just an example. You can see here how this enzyme has a shape right there at the active site that looks just like its substrate, right? Because it literally physically fits in. Of course, what this picture doesn't demonstrate is the chemistry of it. So imagine, for example, I don't know, if this was negative, right? If that portion of the molecule was negative, then you can imagine this portion of the enzyme is probably going to be positive, right? Because they're going to attract each other. Another way of looking at it is maybe if this part of the substrate was polar as opposed to non-polar, then you could probably bet this is also polar, right? Because polar things attract each other. Non-polar and polar repel, right? So not just the shape, but also the chemistry would fit. So what happens is, we're making noise. Let me check on that really quickly. What happens is the enzyme meets up. Oops, there we go. Meets up with the substrate, and we have something called an induced fit. And I have this picture of these people hugging. You're probably wondering why for a while. Now I can explain why. Imagine how a hug goes, right? Like usually hugs start off like this, right? Your arms open. You're like an enzyme ready to take in the substrate, which is the person you can hug. And then once you bring it in for the hug, usually, I mean, some people might say like this for a hug, that'd be pretty weird. But usually people wrap their arms around each other, right? And give a little squeeze. That's a hug. This is what happens with your enzymes, right? It's open. It's a little bit as open as it can be. Wait for that substrate. And the substrate gets in there and it kind of snugs on it a little bit. Gives a little hug. And that is called the induced fit. So definitely understand these words: substrate, active site, and induced fit. Again, I might ask you about them on the exam, but these are definitely terms I'm going to use. And if you don't know what they mean, you won't know what I'm talking about. So any questions about this side? All right, the next side is also very important to understand concepts and for the exam. After the product is released, so again, the enzyme takes in its substrate, right, which is the reactant, then it creates the product, right, through the chemical reaction. And then once that product is released, like we saw in this picture on the right, we started with this molecule, right, the substrate that had two parts to it, and then whatever chemical reaction it was broke it down, so there's two parts, right? The product now has two parts. Just like that picture demonstrates, the products are released, and now that enzyme is ready to go again. So it's not like an enzyme is used once and it's done. It's reusable. Enzymes are not used up in reactions. That's going to be very important, more so for the exam than anything else. Because I'll give you some fake chemical equation that you've never seen before. I'm going to make up a chemical equation. I'm going to say this thing plus this thing plus this thing, arrow, right, gives us this thing and this thing. So in that fake chemical equation on the exam, I'm going to ask you which one of these things is the substrate and which one of these things is the enzyme. The way you can tell which one is the enzyme is because it's going to be on both sides of the equation because it's not used up in a chemical reaction. So again, when you get that test question, whichever is on both sides of that chemical equation, that's the enzyme. Now that's just for the exam. Very often, they're not even in there, right? So very often when you see a chemical equation in real life, when we're talking about biology, they might talk about the enzyme, but very often it's not actually in the chemical equation. Or if it is, sometimes they put it above the arrow, right? The arrow for the chemical equation, kind of indicating that, yeah, this is the reaction, but this is the thing that's making it happen. But again, for the exam, to make things simple, I will have it on both sides of the equation, and that's how you know it's the enzyme, because it was not used up. As we already mentioned when we first started talking about proteins, just like any other protein, these enzymes are sensitive to their environment. Remember when we talked about, I showed you that picture of those amino acids next to each other, and I talked about how changing the environment would maybe unravel that protein, right? If we got too acidic, that would mess up those hydrogen bonds. If we got too basic, that would mess up those hydrogen bonds. If we got too warm, that would really mess up the hydrogen bonds because they would have enough energy for those bonds to just be broken. So anyway, that being said, generally speaking, the warmer things get, the quicker chemical reactions happen. Generally speaking, but there is an optimum range because like I just told you, if you put too much energy into it, you're going to break those bonds. And like I said, when we first talked about proteins, that's called denatured, right? So if you put too much energy, heat, too much energy into these enzymes or any other protein, you're going to break the bonds. So when you break the bonds, it unravels. So if it doesn't have its shape, it can't do its job. And like we already talked about, pH, right? So those, if it's too acidic, you're going to have those H+ ions. That's going to be messing with the hydrogen bonds. If it's too basic, you're going to have those OH ions, right? Also, salt concentration. There's also stuff called coenzymes. Those last two aren't as important, but we will bring up coenzymes a little bit later. In other words, you know, enzymes are very specific, but they're also very sensitive to their environment. And, you know, even though we don't talk about this in this chapter or ever in this course, this is a lot of evolution has a lot to do with this too. Some things are evolved, right? Different organisms live in different environments, right? So there's a bacteria that lives in the hot springs of the Yellowstone, and that's hot spring, right? So it has enzymes that do just fine in boiling water. And we actually use those in this room, not this room, in this building. We use those for something called PCR, right? So we take a little piece of DNA and we can amplify it. And to do that, we use an enzyme that we get from those bacteria because that allows us to heat it up and the enzyme does fine. Anyway, any questions so far? All right, the last thing, and this will be important for the exam, is like I said, I'm going to give you a fake chemical equation. I'm going to say which one of these things is the enzyme. The name of the enzymes almost always end with ACE. So that's two ways you're going to know which one is the enzyme. If it's on both sides of the equation and it ends in ACE, then you know it's an enzyme. Some of the enzymes you're going to learn about in this course are protease, ATP synthase, DNA polymerase, RNA polymerase. All right, all these things you're going to learn about later. ATP synthase, I don't know if I said that one. Anyway, if it ends with ACE, as far as we're concerned, it's an enzyme. And if it's an enzyme, as far as we're concerned, it will end with ACE. Also, and I don't know if I have this written anywhere else, so I'm going to say it now to make sure you know. Not only do they end with ACE. Oh wait, no, it is written right there in front of me. Not only do they end with ACE, but they're also named after very often their substrate or what they do. So again, I'll give you a fake chemical reaction. I'll ask you what the enzyme is, and you're going to know which one is the enzyme because it's on both sides of the equation, and it ends with ACE. And then I'll ask you what the substrate is. And then you just, I know what the enzyme is. I figured that out. And then whatever the enzyme is, remember it's named after its substrate. So just look for the word that looks like the enzyme that doesn't end with ACE. And I'll give you some examples when we move forward. But are there any questions about this slide before I give you a visual example of this? All right, here's an enzyme. This is a real life example. This one's not hypothetical. It's called lactase. Anyone want to guess what its substrate is based on what I just told you? Just remember, enzymes are named after their substrates. So anybody want to guess what the enzyme lactase, what its substrate is? No guesses? You guys are too shy. Lactose, right? Lactose is the substrate. And it really does have that shape, generally speaking. But anyway, so you can see here we have the active site where the substrate can fit. It does. The substrate binds onto the enzyme. The enzyme does its job. It's breaking this lactose down. And if you remember way back from chapter 2, every time we break something down, we call that a hydrolysis reaction because it requires an input of water. Anyway, you can't see it, but we've input the water. We've broken it down. And then the products are what the parts that make up the lactose, which are glucose and galactose. And then again, the products are released. The enzyme is ready to go and do it all over again. I'm going to put a big old X through this just to visually remind you or tell you that this is just an example. I'm not going to ask you anything about this on the exam. You do not need to memorize anything about lactose turning into galactose and glucose. You don't need to memorize that. It's just an example of how enzymes work. And the last word for attendance will be bean. To me, that thing looks like a purple bean. That enzyme looks like a bean, like a green bean, kidney bean, pinto bean, whatever. Yeah, that's the last word for attending. So again, send those emails before 9 a.m. Make sure you include one question about the material covered, and that's it. I'll see you guys on Wednesday. Have a great week.